Hello. Okay. So from continuing from day before yesterday, we are from today we are starting the priority queue, okay? Heap up priority queue from the NeetCode. Okay? So today first problem we are going to solve is loss stone weight. Okay. So basically, I have already solved it my own way, but I don't know the proper solution or the most optimal solution. So for that, let's first go through the solution video from the NeetCode, and then we'll try to implement that. Okay. So let's go through the question. Okay. So loss stone weighted. You are given an array of integer stones and stone I in a weight of ith stone. Okay, we are playing a game with a stone. On each stone we choose the heaviest two stone and smash them together. Suppose the heaviest two stone have a weight of x and y, with x less than or equal to y. The result of this smash is if x equal to y, both the stones are destroyed, and if x is not equal to y, the stone of weight x is destroyed, but the stone of weight y has new weight y minus x. Okay, so at the end of the game, there is at most one stone left. So return the weight of the last remaining stone. Okay, if there is no stone left, return 0. Okay, so basically, from the question, what so, we are given the stone's weight. Okay, what we need to do is get the two heaviest stone, collide them together, and whatever it remaining. Okay, remaining, whatever the remaining is, we need to assign to the heaviest one. Okay, let's say it is 7, weight of 7, it is a weight of 5. So 5 minus 7, that will be 2, then 7 will turn into 2. Okay, so we can even think of it like we have weight of 7 and weight of 5, two stones. If you collide these two, 7 and 5, we'll have 2. So what we will basically do is when we collide, whatever the difference we get, we create another stone of that weight and destroy both of those and add that remaining stone to the list. Okay, so we can simply what we can do is we're going to create a priority queue that is max priority queue. Okay, so basically priority queue is the queue, use heap. Okay, so basically in heap element on the top, if there is a max heap, the element on the top is always greater than its child. Okay, no matter what. Okay, so for the max heap, is the for the mean element on the top is always smaller than element at the bottom. Okay, so when we create a max priority queue, element on the top will be the largest, then element on its bottom will be second largest, and element on the child of the on the third level will be even smaller than these two. In heap, if you create a max heap, like it can be like this. Let's say 5, this can be 7, this can be 6. So this can again be this can be 10, this can be 30. Okay, so basically when we in heap, it's not sure, it's not fixed that it's child object, it's sure that it will be greater, but it will be the highest greater will not be sure. Okay, so like if you have max heap, this is a max heap, all the parent, all the children are greater than its parent. Okay, but in priority queue you can be sure that if the highest will be on the top, the second highest will be, let's say, sorry, 30. You can be sure that highest will be on the top, the second highest will be bottom. Okay, then that will be 7, that will be 6, 5. Okay, something like this. Like in priority queue you can be sure the from up to down we will have the largest to smallest. Okay, but in heap you can also be sure that it will be from smaller to the parent will be smaller than its children, but yeah, but we cannot be like this. Okay, it can be like for these skills also, if parent is smaller than its children, the parent is smaller than its children, but the max is 30, but 30 is not on the root, 30 is not the highest on the root. Okay, so that's the difference between heap and priority queue. Okay, max heap and priority queue. So simply what we're going to do is we're going to create a priority queue using this. Okay, so we'll have 8, then 7, 4, let's say 2, 1 and 1. Okay, so what we're basically going to do is take the top, that will be in priority queue, that will be the largest. So what it is, we'll have a top of like let's 8, then we will pop the top element. So once we pop the top element from the priority queue, it will automatically get the second highest and will make that as a root. Okay, and make the tree itself. Okay, you don't need to worry about if you use priority queue. If you use pop, the highest element will be popped and the second highest will be chosen as the root, and for that, from that root it will again recreate the tree. So let's say we pop the 8, then we'll have 7 as the root, then we'll get 4, 2, 1, 1. Okay, so you can be sure when you pop it will happen. So what we do is we have a y, again we'll pop, so we'll get 7. So we have now x and y, the two heaviest. So again we'll pop, then again the second highest, the third high, the next highest will get the become a root, and a tree will again form as a heaviest. The tree will not form, like we'll know that its children will be bigger than, sorry, smaller than its parent in sequence. Okay, sequential. Okay, so again we'll pop that, then what we'll do is simply x minus y. So x minus y, whatever we'll get, we'll add that to the priority queue, and once we add anything to the priority queue, it will automatically sort it based on the priority. Okay, so we understand like what's going on. So now let's move on to the video.
Hey everyone, welcome back, and let's write some more neat code today. So today let's solve the problem last stone wait. So this is an easy ish problem, I would say, but we're also going to be solving the second version of this problem, last stone weight 2, probably tomorrow or the next video that I upload. So the context is that we're given a collection of stones. Each stone has a positive integer weight, so greater than 0 weight, and each turn we can choose the 2 heaviest stones and then smash them together. Now what happens when we take the 2 heaviest stones and mash them together? Well, in one case, if they are the exact same weight, both of the stones are going to be destroyed. If they are not the exact same weight, then the smaller stone is going to be totally destroyed, but the larger stone is going to basically be the difference between the weights. So for example, let's say we had 2 stones, 5 and 4. This is the weight of the stones. They're not equal, so when we smash them together, the smaller stone 4 is going to be destroyed, and the larger stone is going to be basically a 5 minus 4. That's what its remaining weight is going to be. So we start with 2 stones, and then we get reduced to a single stone. The smaller stone gets destroyed. The larger stone is going to be 5 minus 4. That's a 1. So that's kind of what happens when we smash 2 stones together. At the end, there's going to be at most 1 stone left, and it could technically even be 0 stones if there aren't any left. So what do we want to return? We want to return the weight of whatever stone happens to be left over. If we don't have any stones left over, then we can just return a 0 as the default value. So I will say that this problem is somewhat straightforward. Let's take a look at one of the examples. And the reason this problem is straightforward is they gave us basically all the instructions and the information that we need, and all we really have to do is kind of simulate these instructions. We don't actually have to find a clever way to solve this problem. We just have to simulate what they told us. That's pretty much the best we can do. What did they tell us to do? They told us to always take the 2 heaviest stones and then smash them together. How are we going to get, suppose we had a bunch of stones like this. How are we going to get the 2 heaviest stones? Of course, we could sort the array. That's one solution. But even if we did sort the array, you'll find that it's a valid solution. But when we're taking the 2 heaviest, 7 and 1, we're smashing them together, and then we're going to basically be introducing a new stone, right? So 8 minus 7 is going to be the new stone, 1, and then we're going to maintain the sorted property of this list, we're going to have to insert this in order, which might be a little bit annoying, but I think it is a valid solution. But another solution is going to be using a heap, not a min heap in this case, but we're actually going to be using a max heap because we're going to be taking the max stones each iteration. In order to take this input array and transform it into a max heap is actually an O of n time operation with the heapify function. But every time that we want to actually get the maximum from here, that's going to be a log n operation. And how many times potentially are we actually going to need to get the maximum from here? N times. So n multiplied by log n. That's what's going to be the overall time complexity of this solution. Now, how is it actually going to work? Well, basically, as I mentioned, we're going to simulate. So we're going to assume we have a max heap here. We're going to get the largest stone. It's going to be an 8. We're going to get the second largest stone. It's going to be a 7. We're going to smash them together. We have 8 and 7 smashing them together. 7 is smaller, so this is going to be destroyed. 8 is going to be transformed into a 1 now. So let's just introduce another 1 to this list. And we're going to continue the simulation, right? We're going to get the now 2 biggest stones. It's going to be a 4 and a 2. What's going to happen with 4 and 2? Well, 2 is smaller, so that's going to be destroyed. 4 is going to basically be 4 minus 2, which is going to be 2. So we can insert that into our max heap. So now we're going to insert a 2. Now we are left with, it's a little bit messy, but we're left with a 2, a 1, and a couple 1s. So when we smash these 2 together, we're actually going to be left with a single 1. I won't draw that because I think at this point you probably get the idea. Then we're left with 3 1s. What's going to happen with these 3 1s? Well, 2 of them are going to be smashed together, and then we're left with a single 1 left. And we have nothing left. We have no other stones to smash this 1 with. So when everything is said and done, we will be remaining with a single stone. So we can go ahead and return 1 as the return value. And it could have been a little bit different. It could have been something like, okay, we're left with 2 1s, then they get smashed together, and then we have nothing left. So then if we had nothing left, we could return a 0. But that's not the case in this example. We do end up returning a 1, as you can see down here. This problem is pretty straightforward if you have a decent understanding of heaps and their time complexities. In this case, the only tricky part for us in the code is going to be Python does not actually have max heaps. So we're going to have to use a min heap to basically simulate a max heap. And you can do that by basically, assume we had some kind of heap. We would want 8 to be the maximum value. Then suppose we had some other values, 3 and 5. But this is how a real max heap would work. But if we are actually implementing this with a min heap, it's going to be the opposite of this, but we still want 8 to be the value that we get from the root. So what we're going to do is actually have negatives. We're basically going to multiply every value in the heap by -1 so that the minimum, which is negative 8 in this case, is going to be popped when we want the maximum. And then when we pop this, we're going to get -8, but we can just convert it. We can get the absolute value of this and then just convert it back into an 8. That's kind of how, unfortunately, we're going to have to do this in Python. Minimum, which is -8 in this case, is -1 so that the basically going to multiply every value in the heap by -1 so that the minimum, which is -8 in this case, is going to be popped when we want the maximum. And then when we pop this, we're going to get -8, but we can just convert it. We can get the absolute value of this and then just convert it back into an 8. That's kind of how, unfortunately, we're going to have to do this in Python. In other languages, I think you can just get a regular max heap, but I think that's all the information we need. Now we can hop on into the code. But before I do, let me just give you a very quick word from our sponsor for today, interviewing.io. If you want to get hired at with senior engineers who will give you detailed feedback on exactly what you need to work on. They have the largest network of vetted and experienced tech interviewers in the world, so you can book an interview with as little as 24 hours notice. And the best part, you don't even have to pay until you get hired. Please check out the link in the description below for more details. Okay, so now let's get into the code. Like I said, we're going to be writing the simulation for this problem. And so the first thing we want to do is put all of these stones into a max heap. Now Python does not have max heap, so we're going to put these in a min heap, but we're going to multiply every one of these values by -1. We're going to make them negative. So in Python, what I'm doing right now is basically just going through every single stone and putting it into a list and multiplying each stone by -1. I'm putting the negative of that stone in this list. And now I want to turn this list into a heap. So what I'm going to do is heapq.heapify this stones. This is a linear time operation. So now we're good to go. Now we can start running the simulation. And remember, we want to continue this while the number of stones is greater than 1. If we have 1 stone or if we have 0 stones, that's when we can stop the simulation. But until then, we are going to take the 2 largest stones. How can we get them? Well, we're going to pop from the min heap. We can do that like this, heapq.heap pop from the max heap, not min heap. So pop from stones, and that'll give us the largest, and this will give us the second largest stone. And remember, if the stones are equal, that's basically, we wouldn't have to do anything, right? We just remove these 2 stones from the heap, and if they are equal weights, then we don't really have to do anything. We're not going to add them back to the heap. We don't have to do anything. But in the other case, if the second stone that we popped was less than the first stone that we popped. And why am I saying second stone? Well, because the second stone is going to have a smaller weight than the first stone, or equal weight, right? Because when we're popping the first one, that one is supposed to be the heaviest stone. But we're doing it this way. But remember, we made all the weights negative. So what we actually have to do is the opposite of this case. If second is greater than first, suppose we popped, this is kind of an example. Suppose the first stone had a weight of 8. In that case, we would have a value of -8. And the second one had a weight of 7, and the value would be -7 in that case. Then, of course, -7 is a greater value than the first stone, right? So that means basically this second is the smaller stone, and we have to destroy second. And how are we going to do that? Well, basically, we already popped it from the heap, so we don't actually have to destroy it. All we have to do is take the difference between these two and then add that back into the heap. Now, how are we going to take the difference? First of all, a heap push is how we can actually add to the heap. So we're going to add the stones, whatever that value is. How are we going to get the value? Well, obviously the value in this case would be a 1, right? If we took it 8, subtracted 7 from it, we'd be left with a 1. How can we do that computation? Well, basically you can just take second subtracted by first. If that kind of confuses you, if these negatives and kind of that math confuses you, you can convert these into absolute values if you want. So you can take the first and second and convert them into the absolute value. Then the math will be straightforward. I don't really want to waste too much time writing that code out, and this kind of does make sense to me. So I'm just going to keep it short and concise. I'm just going to take second subtracted by first, which will give us the weight that we want to add, right? We want to add a stone of weight 1. But remember, in our heap we are keeping track of negative values, so I would have to multiply this by -1. The easier way to do this is just to take first subtracted by second, which will give us the exact same thing. It'll give us the negative value that we're looking for. It'll take the difference between these, and that difference will be negative, right? We'll have first, which is -8, plus 7, which is going to be a -1, which is what we want in this case. So I hope that makes sense. It's a little bit confusing, but basically this is our case, and that is the entire simulation code. Once we're done with that, we can go ahead and return whatever the value of the stone happens to be, the remaining stone. So stone at index 0. But don't forget, we actually do have negative values, right? So when we return the value of that stone, we want to return the positive value. So we're going to take the absolute value of this stone. And also don't forget one last edge case. What if stones was empty, right? What if we didn't have any stone left in here? Well, one way to handle that edge case is just to take, before we return to say stones, append a 0. So in that case, if there's already a stone in this list, we'll end up returning that stone because it'll be at index 0. If there's not a stone, then we'll add this 0 stone, and then we'll end up returning that 0 instead. So this basically works out in all cases, which is what I'm getting at. So I hope this was helpful. As you can see, the solution does run, and it is pretty efficient. Sometimes it's more efficient than other times. So I hope that this was helpful. If it was, please like and subscribe. It supports the channel a lot. And I'll hopefully see you pretty soon when we solve the second version of this problem, last stone weight 2, which is a much more difficult problem to solve.
So what I'm going to do is, instead of using max heap, we are going to use a priority. Okay? Simply let's use of type int vector of ints. We're going to do priority queue stones dot
हरेक 12 बजे हरेक दिन 12 बजे त्यो हुन्छ के रे रिन्यू हुन्छ
while we have at least one element, more than one element. If we have more than one element, because if we have only one element, we can just return that. We can just return it as an answer. Okay, we can just return it, like if there is only one element in the priority queue, we will know, we'll be sure that that element will be the last weight of the stone. Okay? So for a while, if there is one element, we need to calculate. If there is only one element, we can push it back. So we will check it while priority queue dot size will be greater than 1. Okay, so while it is greater than 1, what we will do is simply get the top element from the priority group, that will be int x. So what I will do, pq dot top. Once we have top element, what we will do is again priority queue dot pop. We need to pop that so that the next highest element will be as a root element. Okay, so again we
data unlimited हैन you call unlimited data
I will have two highest element from the
1.5 GB 1.5 GB
we will have a topmost element from the priority two heaviest element from the queue. So what we will simply do is simply what we will do, if the first listen, if our x is not equal to y, because if x is equal to y, we have will have 0. So if our x is not equal to y, what we're going to simply do is we're gonna pq dot push x minus y. So if both are equal, we will know that we'll be sure that it will be x minus y will be 0. So we do not need to push 0 because that will not change anything. Even in later equation, that will do nothing. So only when the difference is non-zero, we will add that to the priority queue. Okay. Simply, okay, we do this, we keep on doing this. Okay, so at the end, what we can do is we're gonna check. Let's say there is only two elements in the priority queue. We pop both of those. At last, let's say if you have n elements, we keep on popping and popping and calculating, keep on calculating this. But at last, we'll have two elements in the priority queue. When we pop both the two, we'll get that. So the priority queue will be empty. So if it is empty, okay, we will be sure that the next whatever the answer, x minus y will be the answer for us. Okay, so if first let's do this simply. What are we keep on pushing when it's not zero? Keep on popping while it's size zero. So at last value just return what we return. Let's say we have popped both element. So both the element is popped. So there is nothing on priority queue. So if but both element is popped, but we added an extra element. Let's say there is only two element in the list, two stones. We pop the both, we get the difference, we add it. But what if the both stone weight is similar? So if both the weight stone is similar, we do not add anything, but we have popped. So the priority queue can be empty. So what you do is simply check if so. So if it is empty, what you simply going to do is return 0. Else what you are going to return is what you simply going to return is top element of the priority queue. Okay. So or we can just, instead of, if you don't want to do this, if you want to just return top, what you can do is if at the end, let's say if or pq, if it is not empty, once let's say the two element we have pop is not empty, then we check it, we push it. If the last two element is popped, we can last two, if we are down to last two elements, we are going to simply pop, simply going to pop both of those. It will give us empty, and we're gonna just return x minus y. Okay. For some reason, let's say there is not there is only one element. So most of the time, if there is more than two elements, this code will be run. Okay. But if there is less than one element, we get just top of the element. Okay? So for stones of size greater than 1, this will return the final answer. But if there is only one element, this will return the final answer. Okay, so now let's move on to the next problem. Once again, let's let's give it to the chat and try to get the what do you call using max heap. Okay, using max. How we are going to solve this using max heap? So very close. Nice use of max heap priority queue. So priority queue is already max heap. Nice use of. So there is a couple of logical issues in your code. Okay. I get it. So this was our previous answer. Okay? This was our previous answer. So go to listen if you're listening.
Speaker doesn't know how to
Wrong hand, look at the last process. Which in listen that you never return set the loop, then the loop should continues until everyone zero stone remains. So let me see that. We have already solved like this one. So you can do both any one you like. Okay? So I think the priority queue is a maximum. So maximum is implementing region priority queue by default. Okay. So by default, the maximum is a priority queue. So how about mean heap? So we can use a priority queue and do this. Okay. So to get a mean heap. Okay. So let's move on to the next problem. For the priority queue. So k closest point to origin. So this problem also I have solved it previously, but it's too complicated. Like I solved it by myself, so it's too complicated to understand. So let's go through the solution and try to understand. Go through the NeetCode solution and try to understand how to solve in optimal or best way possible, and then we'll move on to the solving it that way.
Hey everyone, welcome back, and let's write some more NeetCode today. So today let's solve the problem k closest points to the origin. So let's take a look at this example, and you can't really see it well, but they have a couple points. So there's 1 point over here and there's 1 point over here. So we have a list of points, right? We could have a bunch more points, right? Anywhere on this two-dimensional grid. We have an x-axis and a y-axis. So each point is represented by a pair of values. This point is 1, 3. This point is -2, 2, right? And so we could have a bunch more points. And we want to return from the entire list of points, we want to return the k closest points to the origin. Now the origin is the center, which is 0, 0, right? So which of these points is the closest to the origin? And in this case, we have k equals 1. So from these 2 points, we just want to return the single point that is the closest to the origin. And we're guaranteed that the solution is going to be unique, so there's never going to be a tie or anything like that. But it could be, you know, in this case we have k is 1, it could be k is 2, k is 3 or something if we had a bunch more points. So we just want to figure out efficiently what are the k closest points to the origin. Now the first thing is, how do we know how far any given point actually is from the origin? You know, you might remember from your, high school math class, or in this case they actually tell us the actual formula, which does make things a little bit easy. So it's basically taking the x difference, right? So in this case, for this point, the x difference is going to be 1 minus 0 plus the y difference. In this case, the y difference is going to be 3 minus 0. And each of these is going to be squared because, that's kind of how it works. A squared plus b squared equals c squared. This is the formula we're using. So if we want to find c, which is going to be the actual distance, we'll take a squared plus b squared and then take the square root of the entire thing to actually find c. So, finding the distance, we can do that a squared plus b squared, taking the square root. But in this case, we actually aren't required to find the square root because we're not actually trying to return the distance. We're just trying to determine which point is the closest. So, for example, let's say we had something like this that totaled up to 5, right? And we had another one that totaled up to 4. If we take the square root of 2 or 4, that's going to give us 2. If we take the square root of 5, it's going to give us 2 point, something. So we're not required to take the square root because we just want to be able to compare which one is greater, right? Obviously, if 5 is greater than 4, we know that the square root of 5 is also going to be greater than 4. So we're not technically required to actually take that square root. And I don't know why I'm making this such a big point. It's just that it's kind of easier to code it up. Then if we don't actually have to take the square root, we just take the absolute difference between the x, square it, the difference between the y, square it, and then add them together. That will be enough for us to compare 2 points and to figure out which one of them is actually closer to the origin. So once you have that down, how can we actually find the k closest points? We're not just finding the single closest point. That would be easy, but we're trying to find k of the closest points. Well, the easiest and simplest idea that you might think of is just sorting, right? So if we have a list of size n, and for each one of these points, we compute this, take the x difference, y difference, square it, right, and use that value to sort the entire list of points, the time complexity of that is going to be n log n, because we're sorting the entire list. And then once we have that, right, like let's say we had 3 values or something, we just wanted the first 2, which is k, then we can just iterate through the list and find k. So the k is not really going to change the time complexity. The time complexity is going to depend on the n log n sorting. But since we're only looking for k points, right, we don't actually need to sort the entire thing. We just need the k closest points. So actually, this problem can be reduced or slightly simplified if you use a min heap, and that's going to be the solution I'm showing you. If if you already know how to use a min heap, you can probably skip to the coding portion or solve this problem yourself. A min heap is a good way to solve this problem, but I'm going to analyze it for you right now. So let's still take the simplified example. So like I said, the first thing
this series we have already used. We have created our own system, our own comparator, okay, for min heap, okay. So we done this, okay. So this is not an issue, okay. So what can we do? We can just let's just copy this. Let's put it to search and try to ask what is the time complexity of this. So time. Let's do the time complexity of this. What is the type issue first? Or that we need to time complexity. And so time complexity is n log n. So you n log n for optimized. In this case, we'll have n log k. Except for optimized. So let's see the optimized version first. Right? So whatever this here, what it means, we're trying to get point. Try to get a priority queue using the distance of all the elements. Okay. What we're doing is getting the square root of all is the equivalent distance from origin to all the points. Okay? From origin to all the points. So once we get the origin to all the points, the distance, we are using the distance as a priority for min heap. Okay? So once we have gone through all the distance, gone through all the points, we'll have a distance min heap. So what it basically doing is going through the loop, going to the min heap. Okay. We are going to the min heap and getting the top element and popping the top element while k is greater than 0. Okay. So and return that as a result. Okay. So this is a more optimal solution of how to do this. So we'll see this later on once we complete this video.
We're going to do for every point. So we have the point 1, 3, and we want to know the distance between it. So we can say, okay, 1 squared plus 3 squared, which is going to give us 10. So this is, the distance actually isn't 10, but that's going to be the value we use to compare. We're not going to take the square root because we actually don't need to. The other one, negative 2, positive 2 is going to be 2 squared plus negative 2 squared, which is, just going to be 2 squared as well. So taking both of these together is going to be a distance of 8. So plus 3 squared. And we want to know the distance between it. So we can say, okay, 1 squared plus 3 squared, which is going to give us 10. So this is, the distance actually isn't 10, but that's going to
first we will do log n. So this is what n. Once you have n, we are just looking through again n1. So ok. So log o n and ok. O of n and O of k. So why it's say that that happens is n log n. So we need all points. So for all points, we have to take the distance. Okay, for distance, we instead of element at the top and moving the elements. for the moving elements, we have log n.
Be the value we use to compare. We're not going to take the square root because we actually don't need to. The other one, -2, +2 is going to be 2 squared plus 2 plus -2 squared, which is, you know, just going to be 2 squared as well. So taking both of these together is going to be a distance of 8. So the next thing we're going to do is take these, right? Notice how we put the distance as the first value, because when we put this in a min heap, we want this to be the value that we order it by. So we're going to take this and we're going to run the function heapify, which is not n log n. Heapify is actually a linear time algorithm. So it'll basically take all of these, put them into a heap in O of n times. So now, you know, let's say that all of these are in our min heap. What are we going to do? We want to pop from this heap k times, because we want, every time we pop, we want to pop the closest one, which is in this case going to be this point, right? And of course, k in our example is only 1, but obviously this solution could be generalized to if k was 2, 3, or bigger, right? So in this case, how many times are we going to pop from the min heap? Obviously k times. We only need to find the k closest points. And what's the operation for popping from a heap? It's going to be log the size of the heap, which is worst case going to be n. So this time complexity is actually going to be a little bit better. It's going to be k log n. That's why a min heap solution is slightly more efficient, because if k is relatively small, it's going to be a lot better than something like n log n, right? So this is much smaller, this is much faster. So that's kind of the idea. At this point, you probably know how to code it up, but you know, just to finish the example, k is 1. We pop from this one time. Are we going to pop this one or this one? Obviously, this one has a smaller distance, so we pop this one, and then we take it, append it to our result, and we only append the coordinates. The coordinates were -2, +2, right? We don't actually have to append the distance or anything, so this will be added to our result, and then we're going to return that result, right? We only need to pop once, and we can return that. You can see up in the result over here at the top, that's exactly what they did. They just returned a list of 1 point, so that is the main solution. Now we can go ahead and code it up. So now let's actually code it up, and like I said, we're going to be using a min heap. So initially, a min heap is just an array or a list.
Visit it. We have to do this min heap. So the distance where we have created particle of with the and better select. This the distance, we have to select the distance and x and y also. Upward this reverse. This heap size less than or equal to k. If greater than k, we just pop. We know the furthest. So then result. Then while it's not empty, what we're going to do is get the second opposite and keep on copying it. I'm able to understand like this part. So this part, like these are similar to our own problem, like our own solution. So,
three values. We're popping the distance, the x. We can go ahead and return the result that. So I hope that this was helpful. If it was, please like and subscribe.
So let's say first we get. Okay. So for this solution, let's say. We are creating the heap for the size of k. So let's say we have already, let's k is equal to 2. Okay, so if our k is equal to 2, so the first heap will be empty. So first we'll add, let's say size as a, let's say 3, then we will add 5. So we know that these two, if these two are the last elements in the list of given points, this will be the answer. but let's say there is more points. Let's say for the first point we get 3, for second we get 5, for let's say third point, once we get the third point, let's say we get something like let's say 2. So we'll add these two somewhere here. Okay, so once we add 2 over here, we know we need 2 smallest. After adding the 2 smallest, what we will do is we will pop the last element. So we can be sure the last element in the priority queue, if the k is equal to 2 and the size of the priority queue is greater than 2, the last element will never be the answer for that one. So we're gonna pop that from the priority queue. Okay, so let's do the same. Let's create a priority queue. Priority queue of pair of int and vector of int. Okay, as a priority queue. So while what do instead of while, let's do for each points, right? Vector int in point in points. Okay. What you're gonna do is simply let's get the x. Okay, that will be 0.0. Okay, so int y, that will be 0.1. So from the point we get the two index x and y index. Once you have an x and y index, we're gonna calculate the distance. Okay, so int distance will be simply x into x plus y into y. So we didn't have to do the square root of the square root. Okay, you can do the square root, get it at a float and change the pair float and vector type int, but we can do it simply this way. Then what's for the first point, what we're gonna do, then we're gonna add that to the priority queue. So what is it? Push, we're gonna push distance comma x comma y. Okay, so again after adding, what I need to check if our priority key has size has increases more than the k. If okay, if that size is greater than k, if it is greater than k, just what I will say is pq dot pop. So this will this is a max priority key. Okay, so whatever the max value from that is, we'll pop it. If you have made a mean priority queue, let's say we have given a comma and greater than, if you pop, we will have popped the minimum. So instead where whatever it is, we are creating a max. So whatever the top element, whatever the highest element in the priority queue is, will be popped once we add that to the queue. Okay, instead of creating a minimum priority queue, we are creating a maximum priority queue, adding the element to the priority queue, while just keep on adding. Once we get the k element, whatever the maximum distance will be, if there is more than k element, whatever the maximum distance, that will never be an answer, so we'll pop that right? Once we pop the elements, what we're going to do is clear it up, vector of int, vector of c, vector of int as a result. So once we have a result, what we're going to do is loop through while just look through the priority queue. Okay, so pq dot empty, while it is not empty, what I'm going to do is get the top element second, so top element vector. Okay, So order doesn't matter. Okay, so instead of like giving the smallest first, then the largest, the order doesn't matter. You can see that you may return the answer in any order. Okay, so what I will do is where order is rendered in descending order. Okay, so get the top element from the predicate, that will be the largest distance. Okay, from the origin. So let's simply do it. Resulted push back whatever push back whatever PQ dot top element dot second is okay. Once you get the top element, we are ready to the result. Then what do we need to pop the top element. Once you pop the top element, what I want to do is, so that's it. Let's do this. Yeah. While it is not empty. So when we come to it, when this loop will be when we run this loop, we are sure that the PQ size is equal to the K, because we are popping the element from the that. And once it runs K type, instead of doing that, you can do that it for run times also. So, uh, so let's save it as a solution. So it's accepted. It's fine. So it is similar to this one. But so it is optimized towards using max Heap. Okay. So where are you getting let's add a node. Let's add a node. Yes. And, and okay. For this log and log and okay. So we have it. If you want to stabilize the swing, quick shot for we can lower time, but it's already giving optimal solution. But that will not use priority queue. Okay, that's great. So if you go through this solution, they are not using priority queue. So the problem is problems requiring the priority queue to solve it. They are not using priority queue. This is a more faster solution, but how we are going to use priority queue. So so let's move on to the next problem. Okay, we can solve this problem now. So quick setup. By step by step. This. Let's see the solution. There's a quick select, sir. Quick select. So this will be the faster of n. That is complicated. So there's a lot of things that you need to write. More code you need to write to solve this problem. So let's leave. Let's move on to the next one. So kth largest element in an array. Okay. So what's the problem? Let's go through the problem and try to understand it. So kth largest element in an array. Given an integer array nums and an integer k, return the kth largest element in an array. Note that it is a kth largest element in the sorted order, not the kth distinct element. Given an integer array nums and the integer k, return the kth largest element in an array. Oh, let's solve it without sorting. So what you're going to do is create a priority queue. Keep on popping 2 times whatever this highest element will be. What is the time complexity of creating a priority queue? It's, the priority queue, what is the, that is for n. So for pushing it's login, for n elements it will be n login. The total is n login. By default backend by vector. Okay. So building an existing, if we have existing vector and we want to create it, it will be of n. So make heap. If we insert the elements, it will be n log n. If we have already created a vector and directly passing the vector as a form of priority queue, that is make heap construction. That type it will be of n. Okay. So make heap will also work on time complexity. We could put heap function manually. Insert element on 1 by 1. That will be n log n. So what we're going to do is make the priority queue based on this. Priority queue of what you need to return. We need to return the max element of type vector. We need to return maximum. So we need to the largest. We need to create a max heap. Let's create a max heap also. Instead, okay. So once we have created the priority queue, whatever we simply do, while k is greater than, so whatever simply going to do is let's see, result is that will be 0. Return 0. So kth largest. So what you do? The second. So what is the first largest? 6. We pop it 1. Then we have this. So instead of equal to 0, while it is less than or equal to 1. So by default, the highest result will be PQ dot top. Okay. Because let's say if the k value is 0, k value is 1, yeah, this will never run. So this will, if this never runs, we return the whatever the top limit is. Let's say is 1. If it's to the second highest, so what is it? Keep on. This is we pop the first element, for the second element, whatever the top limit is, we're gonna return the. So what we'll do is whatever the top limit is, we will return it by the end of. So that's while k is greater than 1, whatever what we as implemented is get the top limit from the priority queue, that will be the top limit from the priority queue, that will be. No, let's just keep on PQ dot pop. Let's keep on popping. So if you keep on popping the element, well, this time then get the top element, we'll get the result. Sorry, one second. Key minus minus. Right. So we are able to get the answer that we want. Okay. So this was the simple problem using the priority queue. Let's go through the solution from the this one. Get largest element. Okay. So once again, if you go, I think there is another problem, similar problem, top key frequent problem. So this problem can also be solved using particular top key frequent elements. So we create a heap of the max heap and keep on getting the top. Right. So if we, what is the time complexity of this solution that we created previously? They're saying that I do it in n log n. So let's see what is the time complexity of this problem solution. So what has lost basis, but it's okay. Time complexity problem. So for pop it's log n, and we are getting the top key. So that is key log n. Okay. So our time complexity is key log n, which is more efficient than n log n. But what is the time complexity of this problem? That we previously have done using this. So this will be log that's O of n. So once we have count, we are using bucket. Okay, we are creating bucket. That is also okay. So let's see if it is faster or slower than the this problem. What is the time complexity? So our time complexity is of 4 of n. Okay. Because we can solve this problem using priority queue in K. We have solved this problem in K login. Okay, solve the previous this problem in temple city. What is the temple city? Finally, is n log. Okay, n plus K login. So it's slow. It's not L login. So you return inside the loop. Correct question. Let's get the top layer. So we do not need this variable as a result of that's we have just created this to understand like the supplemental result and we are seeing the result. We do not need to do this more optimal. Your return is inside the loop and the brace is brace of mismatched. I pasted the wrong code. Okay, so I basically pasted the wrong code. That's the issue. But final complexity is plus login. And for this problem, the time complexity is of O of login. So this is better. If we use heap sort, it will be login. So what faster let's bucket and balance plus maybe syntax. But when you use Heap, we have and login. This bucket is one. Okay. So the request is one. Interview. If k is small, we use allow. If k is larger, we use okay. Sorry, this is key frequent element, so it's a different problem. I thought top 5. So key frequent element. This investigator is a problem. So key frequent element where is bucket. We create a heap, then we have answer, then we know that the size, how many times it repeats, so that's so as many times it's repeat with that. This is a bucket. Let us send the better first. Okay. So now let's move on to the next problem. Ready. That is task case schedule. Task schedule. So for the task schedule problem, I think it's a design problem. So we are basically not trying to solve the design problem right now. Is it a design problem? So it's not a design problem. So let's try to solve this problem. Let's go through the problem. Task schedule. We are given an array of sorry. 1 second. We need to go through the solution for this problem. Let's go to the solution for this to see if our solution and the solution provided here are similar or is it the optimal? Is the NeetCode has an optimal solution?
Hey everyone, welcome back and let's write some more NeetCode today. So today let's solve the problem kth largest element in an array. So we're given an integer array nums and an integer k. We want to return the kth largest element in the array. By largest, they mean largest in sorted order, not the largest distinct element. So we could have duplicates in this array. And so when they say, let's say k equals 1, right? If k was 1, and let's say this array was sorted, then that would mean we want the rightmost element because we want the first largest element. If k is 2, we want the second largest element. So not the largest element, but the second. largest element. So
care to list 20 element. Let's say there is 2 times. Don't care if it's set 2 times. You just need that. Okay. If you are the distance, we need to remove first duplicates from them. Yes, there's a duplicate. We don't have care if it has a duplicate. We just need the kth element. But if there was a kth distinct element, we need to remove the duplicates from the first. We need to remove the duplicates from this array. Then we need to solve the problem.
So that's how it works. Now, the most obvious solution you probably could already come up with by yourself is just take the input array. It's not necessarily going to be sorted, but we could sort it ourselves. What would be the time complexity? Well, it would be n log n, right? That's the time complexity to sort. And since this is an array, once we sort it, we can instantly check the index that we want. What index are we going to want? Let's say k is 2. What index would we want in nums? We'd want the second largest, right? So instead of the largest, we'd want the second largest. So how would we do that? We'd just take the length of the array minus k. That would give us the index that we want to get to. But this is a medium problem, so you can assume that there are going to be different solutions. Can we do better than n log n? Well, it turns out we can, and one solution is using a max heap. Using a heap will be slightly better because we won't have to sort the entire input array. What we can do with a heap is you can take an entire input array like this one and you can heapify it. You can turn it into a heap, and you can do that in O of n time. But just because we have a heap doesn't mean we've necessarily solved the problem, because we don't necessarily want the largest element in the array. We might want the kth largest element. But just because we have a heap doesn't mean we've necessarily solved the problem, because we don't necessarily want the largest into a. You can take an entire input array like this one and you can heapify it. You can turn it into a heap, and you can do that in O of n time. But just because we have a heap doesn't mean we've necessarily solved the problem, because we don't necessarily want the largest element in the array. We might want the kth largest element. So from that heap, after we've already done an n operation to turn this array into a heap, then we're going to have to pop from that heap k times, because it's a max heap. So we're going to pop k times so we can get the kth largest element. Every time you pop from a heap, it takes a log n operation, where n's the size of the heap. How many times are we going to pop? We're going to pop k times because we want the kth largest. So this is the time complexity of the heap solution. You can see it's slightly better than n log n, depending on whatever k happens to be. So in some cases, it will be better than the sorting approach if k is relatively small. And that's about as good as you can do in terms of worst case time complexity, but there is a solution that's better actually if you want to know.
Sort your log n bad. Let's sort with this log n, then access it with. So we'll have
minus the time complexity. Well, it's now the most obvious solution you probably could already come up with by yourself is just take the input array. It's not necessarily going to be sorted, but we could sort it ourselves. What would be the time complexity? Well, it would be n log n, right? That's the time complexity to sort. And since this is an array, once we sort it, we can instantly check the index that we want. What index are we going to want? Let's say k is 2. What index would we want in nums? We'd want the second largest, right? So instead of the largest, we'd want the second largest. So how would we do that? We just take the length of the array minus k. That would give us the index that we want to get to. But this is a medium problem, so using a heap, turn it into k times so we can get the kth, which happens to be just the average case time complexity. And that's what I'm going to be focusing on. The solution actually can be achieved with O of n average time complexity, not worst case. The worst case actually happens to be n squared. So in the worst case, it's not that efficient, but in the average case, it is pretty efficient. What algorithm am I talking about? Well, I'm talking about the algorithm quick select. It's pretty similar to a standard algorithm that you may know called quick sort. And if you haven't heard of this algorithm, I'm going to be teaching it to you today. If you have, then you can probably implement this yourself. Let me show you how to do that now. So let's take a look at this first example. And like I said, this algorithm is going to be really similar to quick sort. And the main part about quick sort is the partition. So that's what we're going to do first. We're going to take this entire array and partition it into 2 halves, right? We're going to somewhat cut it in half. One half of the array is going to be every value in, let's say this half of the array is less than or equal to every value in the right half of the array. That's how we're going to partition it. So how can we make sure that it's always going to be half? Well, it turns out we can't. That's why the worst case time complexity is going to be n squared. Half? Well, it turns out we can't. That's why the worst case time complexity is going to be n squared, and the average case time complexity is going to be O of n. Because what we're going to do is we're going to randomly pick a pivot. Let's just pick the rightmost element each time as the pivot value. When I say pivot, I mean this value is going to decide what goes in the left half and what goes in the right half. So what we're going to do now, we selected this as our pivot. We're going to start at the beginning of the array, and we're going to go through each element and we're going to compare each element to this pivot value. So for example, 3 is less than or equal to 4, right? So what are we going to do? We're going to make sure to place it in the left half of the array. It's already in this spot, so what we're going to do is basically just swap it with itself, and then we're going to shift our pivot pointer over here. This pointer is basically going to indicate every time we find a value such as this one or this one that's less than or equal to 4, then we can put it in this spot wherever this pointer happens to be, and then once we've done that, we're going to take this pointer and in this spot wherever this one that's less than or equal to 4, then we can put it in this spot wherever this pointer happens to be, and then once we've done that, we're going to take this pointer and shift it again to indicate that, okay, next time we find a value like this one that's less than or equal to 4, then we're going to put the value in this position. So in the actual code, we're going to be doing this in place, but I just drew an extra piece of memory just to kind of help you visualize it. So we're going to take our 3, keep it in this spot. 3 is going to go here. Our P pointer is now going to be shifted here. Originally it was over here, but now we shifted it over here. So now we're done visiting this element. We're going to go to the next element, 2. Is 2 less than or equal to 4? Yes, it is. So we're going to go ahead and put this value 2 in the position where P points at. So we're going to put our 2 over here. P is going to be shifted by 1. So let's put P over here. We find we go to the next element, right? 1, again, it's less than or equal to 4. We put 1 over here and then shift our P value. So 1 goes here. P is going to be over here now. Now we get to our first element. That's not less than or equal to 4. So what do we do in that case? We're going to leave this exactly where it is. And again, we're going to get to the next element. 6 is, again, not less than or equal to 4. We're going to leave it exactly where it is. And before we actually get to the last element, we're going to stop. So at this point, we're basically done going through the entire array, right? And now, so at this point, we're basically done going through the entire array, right? And now our array looks something like this, right? We have a 4 over here. And at this point, what this P pointer tells us is that every element before the P pointer, everything over here, is less than or equal to this value 4. And then every value P pointer tells us is that every element before the P pointer, everything over here, is less than or equal to this value 4, and then every value over here, right, P and, all these remaining elements except for the last one, of course, all of these elements are going to be greater than 4. Elements except for the last one, of course, all of these elements are going to be greater than 4, right? Because all of these are less than or equal to 4, so these must be greater than 4. That's what we mean by partitioning the array. Now notice, just because we partition the array, this is not in sorted order, right? It's not necessary. The halves of the array, the partitions, are not necessarily going to be in sorted order, but they are going to be partitioned so that everything here is less than everything here. And one last swap that we're going to do now is we're going to take our pivot value over here, which we selected as the rightmost element, and we're going to swap it with whatever happens to be at this pointer right now. So let's do that last swap. We're going to replace this value with a 5, and we're going to replace this value with a 4. So this might be a little hard to read, but so the reason why we did that, you're probably wondering, why did we even do the partition in the first place? So now we know, all we know at this point is we have some value at this pointer P. This is the value we use to do the partition. Right now it's over here, and we know that everything over here is greater than it, and everything over here is going to be less than or equal to this partition value, right? That's good. So now what we're going to check is, where is that K value that we're looking for? Where is the second largest value in the array? Remember what we determined earlier, that we can find that target value at the index length minus K, right? So the length of this entire thing is 6 minus K, which is 2. So we're going to go to index 4. This is 0, 1, 2, 3, 4. This is index 4. So all we have determined at this point so far is there are 2 elements on this half of the array, right? So we know for sure that the second largest element must be somewhere here. We don't know for sure that this is the second largest element or that this is the second largest element, because remember, these are not necessarily going to be sorted. In this case, they're not. So we don't know it's over here, but we know it's somewhere in this half of the partition, right? It's definitely not here, and it's definitely not here, right? If the K value is different, right? Maybe K was a really big number, then we'd get length, which is 6, minus, let's say K was 4, then we'd get 2, right? That would tell us that, okay, the target value is going to be in the left half of the array. Or it could even be such that, let's say k was equal to 3. Then we'd get length, which is 6, minus k, which is 3. Then we'd get the value 3. So then we'd go to index equals 3. And then we'd see that this is that index, right? And then if it's ever this case, right, where that value, that target value is exactly at P, wherever that partition happened to be, then we've actually found our result. Do you know why that's the case? It's because we know for sure that this is the kth largest value. In this case, we know for sure right now that this value is the third largest value, because we know for sure that everything in the left half is less than or equal to this value, and we know for sure that there are two values that are greater than this value. So that must mean that this is the third largest value, right? So we found the third largest value, but we're looking for the second largest value. So basically what I'm getting at is we're going to do this recursively. So instead of basically we've eliminated that these cannot possibly be the result. So now we're going to run the exact same algorithm I just showed you, the quicksort partition, on this part of the array until we find that result, until we find k equals to the second largest element. And when we actually do that partition on this, we're going to use 5 as a pivot. We're going to say 6 is greater than 5. Our p pointer is going to be here, and then at the end we're going to take this, swap it with whatever's with p. So then we're going to have an array looking like this, 5 and 6, where this is our partition value. This is where p is at. And like I said, all this is actually going to be done in place. So we will have the ultimate array, and then we're going to look at k, the length minus 2, which is going to put us at this index. Then we're going to have found our result. 5 is the second largest element, because we know for sure there's exactly one element that's greater than 5, right? There's one element that's greater than 5. That must mean 5 is the second largest element. So that's mainly how the code is going to work. So if you recall how quicksort works, it's a little bit different, right? Let's just analyze the time complexity right now. So with quicksort, when you do the partition, then you have to recursively run quicksort on the left half and on the right half, which ends up giving us a average case time complexity of n log n. But in this case, the average case is actually going to be big O of n, because we're not going to be looking at both halves of the partition. We're only going to be looking at most one half of the partition, wherever we know that the target value happens to be. And assuming in the average case, every time we choose a pivot, that pivot is going to be somewhere in the middle of the array. It's going to be middle of the pack, where half the elements are less than it, half of them are greater than it. That's going to give us, you can probably skip over this part, you probably don't care, but just to analyze the time complexity, we're going to have to iterate through the entire array once, right? So let's say that's an n operation. Then we're going to have to, let's say, iterate through half of the array, which is going to be n over 2 operation. Then we're going to have to iterate through half of that array, which is going to be n over 4. This is an infinite series that you might remember from calculus. This infinite series evaluates to 2 times n, which we know is linear. So that means the average case is n over 4. This is an infinite series that you might remember half of that array, which is going to be n over 2 operation. Then we're going to have to iterate through half of that array, which is going to be n over 4. This is an infinite series that you might remember from calculus. This infinite series evaluates to 2 times n, which we know is linear. So that means the average case time complexity is big O of n. That's the average case, but we know that actually in some cases we could have a pivot value. Let's say 6 was our pivot value, right? 6 was here. Then when we partition the array, our p pointer is actually going to be over here. So, and let's say we didn't find the result, then we're going to have to look through pretty much the entire array except one element. And it could be, the array could be organized in such a way that every time we choose a pivot, that pivot is always the greatest value. So basically each time we iterate through the entire array, we eliminate one value. We iterate through the entire array again, we eliminate one value. We iterate through the entire array again, eliminate one value. So that's an n squared time complexity in the worst case. But like I said, the average case is actually big O of n. Okay, that was definitely a mouthful. So now we are ready to get into the code. It's not too difficult. The code, and like I mentioned,
what problem we are not going to solve on using pixel because we have already solved it. It's working, so we do not need to, like, we are just preparing for the interview, so we don't need to do that. Let's go another step of this problem. The task is case one. You are given an array. You are given an array of GPUs tasks, each labeled with a letter from A to Z, and the number n. Each label with a letter A to Z and a number n. That is, GPU interval can be idle or allow the completion of one task. Either the task can be completed in any order, but there is a constraint. There has to be a gap at least an interval before two tasks with the same level. Okay. So each GPU intervals can be idle or allow the completion of one task. Tasks can be completed in any order, but there is a constraint. There has to be a gap of at least n intervals between two tasks with the same level. within the minimum number of GPUs interval required to complete all the tasks. So what is the possible sequence? A, then we go to B, then idle, then again A, then B, then idle, then A and B. So after completing the task A, you must wait for the must wait 2 intervals before doing A. The same applies to the task B. In the third interval, neither A or nor B can be done. So you are at but the fourth interval in the fourth interval you can do A again as 2 intervals has passed away. So first we do A. So now we need to for A to complete we need to wait 2 intervals. So in second interval instead of waiting we do the whatever other tasks is remaining. So we do this to B. Then we again for A we need to wait 2 interval. For B we need to wait again 2 interval. So for A we have waited 1 interval, then we need to again wait 1 interval, then do this. For B we have waited 1 interval, then 2 interval, then B. Okay. So for this it will be A, then B. Yes, then again we can do A, B. We can do A. Not in any order. Okay. A, B, A, again B, and C, D. We can do that like that. A, B, A. 1 interval has passed, then again B, C, D. That will be 1, 2, 3, 4, 5, 6, 7. So with a cooling interval of 1, you can repeat task after one other task. Okay. For this 3. So we'll have A, then we'll have B, then we'll have 2 idles. A, B, then A, wait, then again B. Wait. So application. How can we solve this problem?
टीम में मिलते ना माली वीडियो कॉल करा टीम में मिलते ना माली वीडियो कॉल करा यहाँ है नहीं हो मतलब ऑप्शन से वीडियो कॉल करा
Fourth is NS51. So how can we solve this problem? I don't know how to implement the variable model.
मिल देना मेरा में मिल देना है ना आईफोन का एंड्रॉइड का मिल देना
But I will set it for the most frequent
ये वाला
data
बहुत है
that can be used like application
मेरा में क्या नाम है
decrease the frequency of data variable. Well, like we can solve it like if we use like if we go a little complicated we can solve it like this. We can like what we can do is again will create any heap. Oh, sorry. If we use, let's say, hash map. So for first hash map, we will have the count. Okay, count how many iterations it exists. So let's say 3, and B is 3. So we'll have another heap. Like, for A we have 2, for B also we have 2, and for all the element we have 2. So what we do, we'll take the first element from the heap. So once we add element to the heap, we have added all the element. We need to subtract it. Let's subtract it to 2, then we'll subtract it to the we have A2, B2. So what it is, we will check this heap. So what it is, we take A, any element from the first. Let's take any element. Let's take A. We get to B or A, whatever we want. So let's do. Let's do A. Once we do A, we'll subtract it to 1. Okay. No. Once we we'll move on to the next, whatever the except A, whatever there is. So whatever there is, we'll subtract the previous one by 1. But again, we'll check whatever there is except whatever has already existed. Whatever have already been exist. A and B. Okay. We'll look through this and check if any of it is true or equal to 0. Either 2 or 0. If it is 2, we'll have first one we'll add a 1. Then we do nothing. We accept that one. Whatever. Not accept that one. We'll leave it to that. Then we move on to the next. And if the other elements, see if there except that one, if there is any other element that has 2 or 0. So there is B. So once there is a B, what we do is whatever what it has existed, we need to subtract 1 from that one. So again, we go through this, check if there is any if there is 0 or 2 or 0. If there is no 2, neither 0, we idle. Okay. Once we idle, what we do is whatever comes before it, we subtract it by 1. This will be 0, this will be 1. So again, we'll move on to this. See if there is any 0. So if there is any element that is 0, if there is a 0, once we change any element to 0, we check into this heap if that element still exists. Okay. So this also exists. We again add this to as a 2. Okay. Then keep on doing this. So this is too complicated to implement. I think it's like we can implement it like this, but I think it will be too complicated because we need to first have these, then what are the elements that have already existed before, and go through those so that we can separate one from those. Or we can create a what do you call it? Instead of heap, we can create an array of size 26, and like A as a 1, B as a 2 index, and we can just subtract 26 plus 1. So So let's move on to the next after the break.
అవునా
We can move on to the next problem. Okay.